Hi, guys. Oh, and good morning, Sean. All right. So, you know what? There's nothing particularly in the announcement today. Okay. All I want to say had been said yesterday. Good. So, let's go ahead and look into the topics today. Okay. So, we're still in RDT 3.0. Good morning, Chloe. We just finished talking about the finite state machine of RDT 3.0. And today we'll begin with the examples. Okay. And the first three examples are straightforward. So here they are. Now I'll let you ponder how you like RDT 3.0. In the meantime, let's move on and see a few examples of RDT 3.0 in action. So scenario number one here is the no loss scenario. So everything is going well. Data, ag. So you see, packet 0 being sent, receiver here receive 0 and send back ag 0. Ag arriving at the sender side, receive what? Move to the wait for call from above for packet 1 state. So send packet 1, ag 1, send packet 0, ag 0, and go on and on and on. So this is a very straightforward scenario. Now the second scenario where we begin to see packet loss. Packet 0 go, ag 0 comes back. Packet 1 goes, but dropped. So what's going to happen here? The receiver is not going to receive anything. And the sender side has a timer, right? So that's going to tick, tick, tick until, timeout. Resend packet 1 and restart timer. So ag 1 comes in. Hey, there's a timer going on here, but because ag comes in before the timer fires, so that timer gets canceled. So packet 0 go, ag 0 comes back. So this is the single packet loss scenario. And the third scenario is the ag loss case. So packet 0 gets out, ag 0 comes back. Packet 1 goes, and ag 1 get lost. What's going to happen there is the timer for packet 1 is going to tick and tick and tick until what? Expiration. So this is going to trigger packet 1 being resent, and finally ag 1 gets received, and data 0 being out again. Now what's a bit unusual here in scenario 3 versus 2 is that, packet 1 was actually received already, but it's received again because the ag was the one being lost. Don't worry, because this is packet 1 and this is packet 1. For two consecutive packets carrying the same sequence number, receiver will not extract data and pass it further on. Receiver just send the ag back again, and that's going to clear packet 1, and therefore packet 0 can go on further. All right, so three straightforward examples. No loss, loss at the sending direction, loss at the receiving direction. Now, the last example is a little bit trickier. It's called the premature timeout case. And you will see here today. The question I asked yesterday, would you prefer when there's a duplicate ag receive, the sender just do nothing or not? Okay. You will see the trade-off of doing it versus not doing that. Scenario number 4 is to illustrate this case, premature timeout. So that is when the timeout interval is this long, but the ag and data takes a long time to take a round trip back. All right. The scenario goes like this. Packet 0 goes, ag 0 back. Packet 1 goes, ag 1, takes longer than usual to come back. So at this time point, timer expires and packet 1 here gets retransmitted. So packet 1 gets retransmitted before ag 1 can come back here. Right. So when packet 1 gets retransmitted, timer for packet 1 is restarted. But the good thing is, hey, ag 1 actually just, arrived. So from the sender's point of view, what's going to happen there is sender thought, ooh, ag for the packet I just sent has arrived, so cool. Cancel the timer and send the next packet. So packet 0 goes. And that's going to trigger ag 0 and come back. And data 1 goes, ag 1 comes back. Data 0 goes, ag 0 comes back. All right. Well, I hope it's just that easy, because we are actually not yet talking about when packet 1 arrives at the receiver, what's going to happen? Well, receiving packet 1, And receiver there will see. This is a duplicate because I just received packet 1, right? So this is duplicate. Ignore it. Don't pass it up to the application layer. But still generate the acknowledgement to ensure that the sender is notified. So ACK1 will travel back. Now, sender here received ACK1. That's right after packet 0 is sent. What does that mean? Well, the sender there receiving a corrupted ACK or an acknowledgement that's not quite in sequence number that's expected, then it's probably a negative acknowledgement. So corrupted acknowledgement, negative acknowledgement, that should trigger retransmission in version 2. But in RDT 3.0, what do we do there? We actually ignore it, right? So some of us are not very comfortable about just simply wait until the timer. But you see here, hey, this will actually not trigger any further packet being generated. Okay. You'll see an advantage in the next scenario, where if we run RDT 3.0 with quick retransmission when there's ACK corruption or negative acknowledgement. So you see here, delay ACK, timeout expires first, packet 1 goes first. And ACK1 there generates packet 0 to go and so on and so forth. Okay. So this generates ACK1 to send. But if, we are not running RDT 3.0, but an RDT 3.0 with what? Retransmission upon corrupted ACK or a negative ACK, then we send what? Packet 0. Okay, again. Because obviously packet 0 is corrupted, therefore we get ACK1. So retransmit packet 0. And that's going to trigger another ACK0. You see, packet 1, ACK1, packet 0, ACK0, ACK0. So for every data packet, for every ACK packet, there's going to be what? A parallel sending, duplicate of it. Is that good? Even though we try to retransmit early. Not that good either, right? Comparing this case and the previous case. So a trade-off in the design of RDT 3.0 there. Okay, we thought that, hey, delay everything till the timer expire is not that smart. But we ended up saving bandwidth in the end, even though the retransmission is a little bit late.
Yeah, so you see, sometimes reacting fast might not be the best thing to do. You see, people's first impression can be very often wrong. All right, so hey, welcome Doris, Pearl, Kevin, Vincent, and David. You guys are just in time for the first quiz today, okay? Sorry, I did not say that on the topic slide here. Next is, in fact, quiz 20. Okay, let's get familiar with the RDT 3.0. How about that? All right. So this is what you're asked to do. Quiz 20. RDT is to handle the packet loss case in addition to the bit error. Okay. So on the left, you see the sender side of the finite machine. Right, the receiver side of the finite state machine. Just very similar to some of the previous quizzes regarding RDT 2.2, 2.1. You will be telling Polly the finite state machine transitions that are triggered in sequence. Okay. Scenario 1 is this. We always start from the initial state, sender's initial state here, as indicated by the dotted line. Receiver's initial state here. And scenario 1 is very straightforward. Send one data packet, but the packet is lost. Okay, tell me the transitioning sequence. Scenario 2, which is independent of scenario 1. Again, we start from the sender side initial state, receiver side initial state. Send one packet. And the packet is received with a bit error. Okay. So what would be the sequence of transitions triggered in this scenario? It's not a packet loss scenario, but you will see that the sequence of transitions triggered different from RDT 2.2. Okay. All right, now let's go to W9, quiz 20, which is right here. You guys have 5 minutes to work on this quiz. All right, let's go. In fact, Polly needs to work on this as well because she changed the quiz a little bit. And needs to make sure that she know what to expect from you guys. By the way, guys, make sure that you finish all the transitions until the system stabilizes. Okay, so scenario runs in one packet, but it's lost, right? There will be also transitions trigger until this packet finally gets delivered. Okay. All right, so hey, it turned out that it's so tough. None of you are able to complete the quiz by the time allotted. So it's okay. Oh, okay, I see there's a teammate. And team 9. Okay, let's see. T1 first, and then the packet is lost. Therefore, at the sender side, T3 is triggered, right, eventually. And the packet is sent. Therefore, the receiver, receiving packet triggering transition 11 and send an ACK back. The sender here, T4 triggered, and the system stabilizes. For the second scenario, T1, okay, and then, oh, hey. Yeah, okay, so the packet is not lost, so the receiver will be receiving the packet, but there's a bit error, therefore triggering T14. Very good, very good. And triggering T14 means that a duplicate ACK is sent back to the sender. So that will trigger which transition? T2, exactly. Okay, and T2 essentially does nothing, right? So eventually T3 is triggered, the timeout is triggered, and the packet is sent to the receiver. T11 triggered, and then T4 at the sender side triggered. Very good. Yeah. Great. And you know what? Let's come back to the lecture. You see, finally, RDT 3.0, it's a working reliable data transfer protocol who works well with bit errors as well as packet losses. But you know what? There is an issue still in RDT 3.0, and it's in fact a performance issue. Okay, so the next video is a little bit long, 6 minutes, and trying to illustrate what the performance issue is.
RDT 3.0. We spent quite a lot of time talking about it, and finally it seems to be working for the bit error case and the packet loss case. And you know what? It works indeed, okay, but it does not work that well. Okay, let me use this example here to explain. So let's suppose we have a pair of sender and receiver. In between them, there is this link, 1 gigabits per second. And the propagation delay one way is 15 milliseconds. And between the sender and receiver, the packet size is 8,000 bits. And that is the equivalent of 1 kilobyte. So this is very typical of a TCP connections packet size. And you see also earlier doing the trace routes, 15 milliseconds is very typical between two routers on a local area network. And 1 gigabits per second link, this is very commonly seen. Some of the Ethernet connections are actually 10 gigabits per second already. Now, let's try to calculate. First, the transmission time. Well, you learned already in chapter 2, right? It's the packet size divided by the transmission rate. So packet size, transmission rate, 1 gigabits per second. And we get 8 microseconds as the transmission time. Now, the performance we'll be looking at here is this, the utilization of the link between the sender and receiver. Okay. If this is high, that means, ooh, sender is actively sending all the time. So usually the throughput is going to be better. Okay. But if the utilization is low, the throughput is not going to get any better. All right. Now, in order to calculate the utilization, let's recall how RDT 3.0 works. We send from the sender one data packet, and the sender there stop and wait for data to travel to the receiver. Receiver sends back an ACK, and ACK travel the network again back to the sender. And that's when the sender can decide whether to send another data. So sender there again stop and wait until data travel to the network, ACK travel to the network, and then send another one. So you see that the sender there is working in cycles. Stop and wait, stop and wait, stop and wait. And each cycle, it's using this much amount of time to transmit actual bits and this amount of time, so plus the round trip wait entirely for the entire cycle. So this is 0.008 millisecond, and this part sending the packet and then wait one way and another way. And here I'm ignoring the add packet transmission time because add packet is usually just very small. Okay, so that's one round trip time plus packet transmission time, 30.008 millisecond. So overall utilization on this link is very, very low, 0.00027, too many zeros. And if I illustrate the scenario I just described there, sender, receiver, and this is timeline. Okay, at time 0, first packet bit is transmitted. So right here, first bit goes onto the link, and it takes this amount of time. That is the time to transmit all bits on the packet. So last packet bit transmitted is right at this time. Okay, that is the packet transmission time, L divided by R. And these bits, it's going to travel halfway to the receiver and another halfway back to the sender. So first packet bit arrives right here. This is what? The propagation delay. Okay? And this is also propagation delay. So 2 propagation delay plus L divided by R. This is one cycle. Within a cycle, only this amount of time sender is being active. Okay, only this amount of data is being transmitted, while the entire duration, right? The sender can just keep pushing bits out, okay, onto the network interface. So you see again, the network utilization, L divided by R over the entire term, RTT plus L divided by R. Very low utilization. And that low utilization can be translated here. The throughput on the 1 gigabit link is only 270 kilobits per second. This is not even enough to send any video that would be sensible. So you see here, RDT 3.0, the design itself, although it works, but it limits the use of the physical resources. Okay, we're only sending one packet and then stop and wait until we can send another one. Now that I show this plot, then you know, obviously to increase the utilization is to send multiple packets per round. Indeed. So let's look at the plot in a bit more detail, just like we did in the previous slide. So sender, receiver, and timeline again. So this is the time we send the first packet, the end of the first packet. This is the time, first bit arriving at the receiver, last bit arriving at the receiver. At this point, the receiver can send back acknowledgement. So this is the time the acknowledgement arrives at the sender. This is the sender can begin sending the next round of packets. So how long is a round this time? Well, this is one-way delay, right? This is also one-way delay. So round trip delay plus L divided by R. So the same. In each cycle, we now send multiple copies of packets. So now we're sending 3, so 3L divided by R, right? So utilization is now 3 times higher than the stop and wait scenario.
All right, so now you see RDT 3.0, there's nothing wrong with it for this type of stop and wait RDT. The only issue with it is that it's just very low utilization. So the performance in terms of throughput is low, okay? And that is why we want this new type of RDT called pipelined RDT. We send multiple packets in a round, okay? So let me introduce this new type of RDTs, and you will see there are 2 flavors of pipelined RDT. And Polly will also give you a detailed overview of the 2, and this is a very important video you want to pay attention to. Pipelined RDT.
And this takes us to this new class of RDTs called the pipelined protocols. Okay. What it said is, let me repeat myself, the sender allows multiple packets being sent per round, okay, or multiple packets in flight. By in-flight, I meant that these are just data packets going out. They are not yet acknowledged. So it's illustrated better here. So this one on the left is stop and wait. This one on the right is the pipelined RDT. So we see multiple data packets go, not yet acknowledged, and their acknowledgements will come back in a sequence, okay, in a round to the sender. Okay, so a range of sequence number needs to be increased. So previously in RDT 3.0, we used just one bit, right, 0, 1. But now we need to allow multiple packets going out simultaneously. And we need to make sure that we acknowledge each of these packets. So we need to tell each of these packets in flight apart. The sequence number definitely needs to be expanded. And we'll need buffering at the sender and the receiver side as well. Because, hey, what if multiple of these packets in flight are dropped? They need to be retransmitted again. So buffer definitely at the sender side is required to store those packets that are not yet acknowledged. Receiver here will also need buffer space because hey, when this packet is lost and there's other packet coming in subsequently, should we keep them or should we drop them and have the sender retransmit again? And what about these other packets that has already arrived? Okay, so there's some buffer space also, okay, needed in order to address different needs of different designs. So buffering required, a longer range of sequence numbers required. Okay. Now, in the next few slides, what we're going to introduce are just two different flavors of these pipeline protocols. So they are the big categories. First is the go back end. The second is selective repeat. Now, one can, of course, further tune the go back end so that it works slightly differently. Hopefully, the second version works slightly better than the fundamental version. Similarly for the selective repeat protocols. Okay, so here's the overview slide that contrasts the two big categories of pipeline protocols. On the left, the go back end. On the right, selective repeat. Right? They are the same this way. Okay. Both of them allow having multiple packets in flight in a round. Okay. Well, that's the basic ideas of pipeline protocols. They must be the same this way. And then everything else will be different. First of all, okay, what the sequence number in the ACK packet means, very different. One is to indicate I'm acknowledging an individual packet. So when the receiver in selective repeat sends an acknowledgement, that sequence number in the acknowledgement is to acknowledge exactly the data packet carrying that sequence number. But for go back end, the receiver sends back acknowledgements, but the acknowledgement carries a sequence number such that all the data packets before that sequence numbers are acknowledged. So this is a bit odd. Okay, so that one sequence number seems to be acknowledged all the packets before that. But the fact is that what the receiver is doing is this. The receiver will not add packets if it arrives and the receiver finds that there's a gap in between. So packet 1, 2, 3 missing, 4. Okay. When 4 arrives, the receiver does not send back acknowledgement 4. Instead, it sends acknowledgement 2 because there's a gap in the middle. So what the receiver of go back end here is saying is, I'm actually telling you to which point I do have consecutive receive data packets. So the next one is, the beginning of a gap, definitely. And the two categories work also very differently here. Timer. Okay, if you recall in RDT 3.0, we need a timer in order to tell whether a packet is dropped or not. Yes, go back end and selective repeat, both of them implements timer. Okay, but in selective repeat, there's one timer for each packet that is still in flight, not yet acknowledged. Okay, so one timer, one packet. But for go back end, there's only one timer for the oldest unacked packet. So in one round, there'll be a lot of packets being sent, multiple packets being transmitted. Okay, there's going to be just one timer for the oldest unacked, meaning if you send one flight out, there's just going to be one timer for the first one in that flight. Okay. And if the first one is acknowledged, there'll be a timer for the second packet that is now the new oldest packet that's not yet active. Okay. So one timer for a flight of packet in go back in. And the last difference is this. Okay. For selective repeat, when timer expires, the sender only retransmit the unact packet. So whatever that timer says, if this is for sequence number 10, then it only retransmits packet 10. But in go back in, when the timer expires, it's going to retransmit from that oldest unact packet. So all the unact packets from the oldest one to the newest one. All right, so each timer is going to trigger retransmission of the rest of the flight of the packets.
All right. Which one do you like better? Given the overview, the go back in or the selective repeat? Okay, so let me collect the first impression again. Those who seem to like go back in better, okay, type 1. Those who prefer selective repeat, 2. Okay, wait. No. Guys. Those who prefer go back in, just type GBN. Those who will prefer selective repeat, type SR. Okay, let's see. Okay, so while you are making the decision, next, Polly will be giving you the details of each of the protocols. And the first one is GBN. Okay, I see. You know what? Hey, yeah, SR and go back end. I think half-half. Very interesting. I'm very happy to see that you guys are opinionated, meaning you have your own way of thinking. You have your own preferences. Guys, that is very important, okay? You do want to listen to other people, so you have references. But you want to also build your own system of thinking, all right? Very good. Interesting, isn't it? Guys, now look at each other's preferences. Some of them think differently, but some of them think the same as you. Interesting, isn't it? And again, back to the lecture that Polly introduced go back in. This first video, unfortunately, needs to be long. I think it's probably the longest throughout the whole semester. It's close to 9 minutes because go back in being a one act for the whole flight of packet. The way we interpret the sequence numbers needs to be careful because it's somewhat complicated. Okay, so this first video, 9 minutes. All we want to say is to give you what how we number the packets. Okay, and that those numbers are called the sequence numbers. Okay, and it's quite complicated. First video, go back in the sequence numbers.
Now let's look closer into the first categories of the pipeline RDT, the go back in. So this is just the sender side, and we'll come to the receiver side in a couple slides. And first thing first, the packet sequence number in go back in. If you recall in RDT 3.0, we only allow one data packet goes in out without being acknowledged, isn't it? And in that case, we just need one bit sequence number to tell the old packet and the new packets apart. But now, go back in being a pipeline RDT, which we allow multiple packets being out in transit without being acknowledged. So your intuition should also tell you that, hey, you need a higher number of sequence numbers to tell all these in-flight packets apart. You are correct, and we now definitely need more, and k here is obviously larger than 1. Okay. Now, having k bits in the packet header, okay, as the sequence number field, then you see the sequence number can range from 0 all the way to 2 to the power of k subtracting 1. And next, in go back in, or generally the pipeline RDT, we do have this thing called the sending window. And the sending window is usually associated with the limit, okay, we call the n, or the sending window size. Okay, so n here is to limit the number of unact packets allowed. Right? And go back in, this is the number of consecutive unact packets allowed. It's also illustrated here. Okay. from the first packet in flight to the last packet in flight, the max range is n. All right, so at any given point in time, we allow only up to n packets being in transit, not yet acknowledged. And so you see here, this thing is also called the sending window, right? And n here is the sending window size. Now let's take a closer look at the plot over here. So each of these slim rectangles are packets. So the green packets are the very early packets that are already sent and already acknowledged. So this is in the middle of the sender transmission, as you see. And yellow packet, starting from here, the send base. So this is the first packet that is being sent out and not yet acknowledged. And there will be a number of these. So yellow ones are the packets already generated and sent, but not yet acknowledged. Now, depending on the application level source, the message could be large or small. Okay, so this is illustrating a case when the message is not that large, meaning you don't need to generate that many segments at the transport layer to cover the entire message. So potentially, within the limit n, we might have some sequence numbers that allow us to generate packets to send out, but we don't really need them. So the blue ones are usable, but not yet sent. Okay, so essentially, yellow plus the blue ones should be less than n. All right. Now, to indicate the beginning of the usable packet sequence number, we use yet another variable, the next seek number. Right? So send base, or sometimes I just call it the base, okay, is the base of the sending window. Next seek number is the next available sequence number that we can generate data packet within the window n. All right? And the last one, so these blank ones are simply outside of the window limit, so not usable. Right? And here, let's assume, okay, send base here, finally receive an acknowledgement, and it's acknowledged, so we turn this into green. What do we do here? Now this one is green, isn't it? So send base is only to indicate the first unACK packet, so we actually need to what? Change it to this packet sequence number. Right? As a result, we shift the window, and it's beginning from here, and include the next blank packet and turn it what? Blue. So the window is actually sliding over by one packet. Okay, so such a window is also called the sliding window mechanism. So when acknowledgement packet is received, you see these yellow packets turning green gradually, okay, and the window sizes is sliding over and then casting more blank packets into blue ones. All right. Just to make sure that it's clear, send base is the variable in go back and sender that always points to the base of the sending window, which means it's always the first yellow packet's sequence number. So the send base will only be changed when the first yellow packet is acknowledged and turned into green. So send base can no longer be pointing to a green packet, and as a result, it needs to be moved to the sequence number of the first yellow packet now. Right? And you see window then here is sliding over by one. The next seek num is always pointing to the next sequence number in case we need to generate a new data packet. So in this scenario, it's pointing, of course, to the first blue packet that is useful and not yet sent. So because when we get a call from above and if we need to generate a data packet, then we'll turn this blue one into yellow. And the next seek num is going to be shifted over and reassigned to the first blue packet after sending. And we do not shift the window size at all because the send base is not changed, and the n here is a constant. But be careful though. There'll be scenarios where, hey, all these blue ones are actually yellow, meaning, the sender does have large message to send, and we are actually exhausting the entire window size to send the message already. In that case, the next seek num will be pointing here at a blank packet. That is the next available sequence number to generate a data packet. But it's not quite yet pointing at the blue one because, there's no blue packet at all. All right, so next seek num, to be very precise, it's just to point into the first sequence number in case we need to generate another data packet. The rest of the Go backend you heard a little bit already about. The ACK, the sender received, is going to be a cumulative ACK. Okay? What it means is that in the sequence number of the cumulative ACK, it indicates all the data packets before this number n are acknowledged. Okay, so all packets before n, including n, are green. All right. Now, if the sender receives duplicate acknowledgements, so hey, ACK n has already been received, but the next moment, another ACK n is received. What does that say? If you recall earlier, yeah, that usually meant, oh, packet n+1, there is a gap at the receiver. And receiver does not send acknowledgement up to sequence number n if there is actually any gap before it. Right? So receiving of a duplicate ACK at the sender side indicates, yeah, whatever n is +1 is a packet that's missing. Timer. Yeah, there is only one timer for an entire flight of an ACK packet. So it's a timer associated with the base, okay, of the in-flight an ACK packet train. Okay, so that is essentially this. Yeah, the oldest in-flight an ACK packet is always indicated by the send base. In a way, yeah, there's a timer associated with the send base, essentially. Whenever the send base is changed or whenever the send base is refreshed, we refresh the timer or restart the timer. If it's a bit unfortunate and we do have packet loss such that the timer needs to time out, then we retransmit the entire flight of packet, starting from n all the way to the highest number that's not yet ACK. So that means starting from the send base all the way to the last of the yellow packet. So timeout indicates the entire flight of the yellow packets will be retransmitted.
All right, and that takes us to quiz 22. Yeah, so let's exercise these sequence number stuff. Essentially the send base, the next seq num, and the first blank packet. Okay, by the way, in the video, Polly talked about those packets that sequence number we cannot use at all as blank packets, but in quiz 22, they are the gray packets. Okay, so we still have the green packets that are the packets that already sent and acknowledged. And we have the yellow packets that are sent but waiting for the acknowledgements. Okay, and send base is right here, equal 23. And blue packets are the sequence numbers is that we are allowed. The sender is allowed to send more data, but there's not that much data from the application layer. Okay, so some of these packets in the window size n can be blue. So that's available packets to send further. So the first blue, the next seq num is now 33. And the first blank or gray packet is 39. Okay, so tell Polly, okay, the sequence numbers of these three variables in scenario 1 being, starting from these values, if we send 4 more packets. So what are the values of send base, next seq num, and first gray packet after sending 4 more packets? Q2, which is independent of Q1, what would be the values of these three variables after receiving the ACK for, hey, packet 28? Would send base change? Would next seq num change? Would the first gray packet change? Similarly, Q3, again, independent of Q1, Q2. Okay, starting with send base 23, starting with sequence number, next seq num 33, and first gray 39. And suddenly receiving the ACK for 32. What will be the values of these three variables? Good? Yeah, now let's go to W9 and channel 21. Week 9, quiz 21. And you guys have, let's say, 3 minutes, okay, to work on this. Polly needs to work on this as well. Is the quiz was changed a little bit. Q1. 4 more packets. Ooh, nice. Yeah, I guess, yeah. Very good. You guys are following. For Q1, do I have 23, 37, and 39? Yes, I do. 29, 33, 45. Exactly. By the way, you can also infer n, isn't it? Yeah, that's exactly 16. See, 17th, 23, 37, 39. 29, 33, 45, 33, 33, 49. Very good. Yeah, very good. Happy to know that you guys have got it. So that is go backend, how go backend sender account, right? The beginning of a flight, right? And in case there are new data, which sequence number to start. Okay, beginning of the flight does not mean that what the next available packet is. Okay, and because the window size is also limited, so there needs to be like the first gray packet number to limit the amount of packets that can be generated. All right, so sequence number and the 3 variables to track all the sequence numbers that is necessary for go backend to work. And now back to the lecture. We see go backend sequence number. Now we can start talking about the mechanism. And so Polly will be introducing go backend's finite state machine gradually in 4 stages. All right. The first stage, pretty brief, because we'll be essentially reviewing RDT 3.0. Okay, so that you can associate better why in go backend sender side finite state machine there are also 4 transitions. So starting from the first video review of 3.0.
Go backend sender's finite state machine. Before we start talking about this, let me review RDT 3.0 sender's finite state machine. And here it is, the RDT 3.0 sender. Okay, so we're starting here. Okay, and there are 4 typical transitions: 1, 2, 3, and 4. So first is to get a call from above. We generate the packet starting from packet 0, send it out, and then start the timer. The other is getting a feedback from the receiver. If it's not corrupted and it is indeed the egg we're expecting, then that's a positive acknowledgement, so we stop timer and move on to send the next packet. Third is when it's a little bit unfortunate, the packet is not correct or not arriving at the receiver, timeout will be triggered. So we retransmit the packet and start the timer again. Last one is when you get the feedback, it's unfortunately corrupted, then we do nothing. So we kind of ignore these two conditions on purpose. The second condition is, yeah, we get an egg all right, but this is what carrying 1, which indicates this is a negative acknowledgement. Right? So in these two cases, instead of quickly retransmit, we just ignore. Right? So this is a quick refresh of RDT 3.0.
All right, so you see there are 4 transitions, right? Sending of a new packet, receiving of a new egg. And then there are 2, right? One is receiving of a duplicate egg, and the other is what? The timeout of the data packet you just sent. So if we merge the wait for call from above and wait for egg from below into one state, then you also have 4 transitions. Yeah, that is exactly what the sender side of go back end's finite state machine looks like.
In go back end sender finite state machine, we also have these 4 transitions. Getting a call from above, receiving feedback from the receiver, and it's not corrupted. Having the timeout event, as well as getting feedback from the receiver, but it's corrupted. Okay, very similar. And then we go through them one by one. Now let's start from the getting a call from above transition here. Comparing to RDT 3.0's getting call from above transition, this one is pretty long. Yeah. And it starts from a if-else condition check. And the condition is this guy here. If the next seek num is less than base plus n, so base plus n is what? The window range, isn't it? If the next seek num is within the range, that means, okay, we can now generate still some data packets. So, makes sense. We go ahead and create the packet using the data from the application layer, generate the checksum for the data, and then give it the sequence number. Okay. Here. We are now using an array of send packet here to store all the packets being generated. This is because go backend is a pipelined RDT, meaning there will be multiple packets in flight, so they'll be generated, being transmitted, but not yet acknowledged. So these send packet will need to be stored temporarily at the sender before they are acknowledged, because chances high that you need to retransmit it somewhere later. Okay, so we need an array instead of just one packet there to store the packets that are in flight. Next step, send the packet out. Oh, and then we need to start the timer, right? This is to handle the cases we could have packet losses. Just like in RDT 3.0, the difference to RDT 2. something is to have these timers. So we need to start timer, definitely. But in go back end, we have one timer for the entire flight of an egg packets. So we need to check, right? We cannot be starting a timer for every data sent. So here we're checking. If the packet we are now generating is indeed the base, the first yellow packet, because the timer in go back end is associated with the first yellow packet, so associated with the base. So only when the packet we are generating is the base, then start timer. Otherwise, don't. So this ensures that we have only one timer for one flight of an egg packets. And the last is straightforward, just increment the sequence number by 1. So this is if the next seek num is within the window. Otherwise, yeah, refuse data. So this is telling the application layer process saying that, hey, I cannot be sending more data packets. So you hold on and you try calling the RDT send after some time. And the second one that we'll examine is this guy here. All right, so this is supposed to be the case where we receive acknowledgement. And it's a new one, therefore we could move on. All right, so let's take a closer look at how the move on is like in go back end sender. First of all, the checking condition. Yeah, get the feedback packet coming from the receiver from the lower layer. And if it's not corrupted, oh, good. So the feedback packet is not corrupted. So this must be one of those what? Cumulative acts. So inside the act, there's going to be carrying a sequence number. So why don't we get that sequence number out? So get act num. Okay, so this is a new function called introduced into go back n's finite state machine. So that is just, a bit abstract, but what it does is to get the sequence number in the cumulative act packet here. All right. And we simply change the base to that sequence number plus 1. All right. So this is the first packet that is an act. Hey, makes sense, right? Receiver sends a cumulative act. So that act carries the sequence number n, which indicates all the sequence numbers before that, including n, are acknowledged. And the n plus 1 is the first in the gap in the receiver. The first one, that act cannot be acting. Okay, therefore, base is assigned to that value. Okay, makes sense. Oh, but we check. So just like in the generating data part, there are a lot more check. Being careful here. If the base is nulled, the next seek num. What does that mean? Base should be the first yellow, and next seek num should be the next data that is allowed to send. But next seek num cannot be a yellow packet, right? So if they are the same, that means there are no yellow packet at all in the window. Okay, which means all the packets that's not yet act at this point in time are already act. Okay, so stop timer because there's no pending packet, okay, waiting for acknowledgement. Otherwise, restart timer. So we receive a cumulative act. The base is reassigned such that it's pointing to the first yellow packet. Okay? And so we refresh the timer for the first yellow packet for the base. Okay? So restart timer. Right? So the only thing that's a bit odd is this. There's an if condition to check whether we should stop the timer because all standing packets are cleared. All yellow ones suddenly turn green. Or we need to refresh because the base is either refreshed or changed to a new value. And therefore, we need to restart the timer, okay, for the refreshed first yellow packet.
All right, so you see that in go back in, every duplicate act will also refresh the timer. Okay, it will actually make the sender of go back in wait for even longer when there's duplicate act. All right, and you know what? Sorry for missing the break time, but it's okay. I'll give you the break time 10 minutes in full. So we'll take a break now and resume at 11:27. Okay, see you in 10 minutes. Oh, hey. Let me try this. Okay, all right. So there was a question from Peter during the break. Yeah, so in S2 here, we send one packet. And the packet is received with the bit error. So at the receiver end here, packet is received. But there's a bit error. It's going to trigger T14, right? And the end action that T14 is going to take is to do this, UDT send packet. But you know what? Send packet is not yet initialized, right? So you know what? When the receiver is initializing itself, the send packet is initialized to ACK1. Okay. Of course, the checksum will be really weird. Oh, actually, no. The checksum will be just the ACK packet's checksum. Okay. Good. So RDT 3.0, the initialization phase will be a little bit different from the RDT 2.2.1. Okay, good. Now, back to the lecture. So, 4 stages to go through finite state machine of go back in. We're just done with the first 2. The third is what? In the finite state machine of go back in, there are 2 more transitions. The center side, there are 2 more transitions we have not yet talked about. The duplicate ACK and wait, 2 more? Yeah, I think so. Duplicate ACK and the timer.
And the third transition is straightforward. It's actually very similar to RDT 3.0's timeout event. Yeah, we restart the timer and retransmit the packets. In RDT 3.0 sender, we retransmit only 1 packet, but this time in go back in, we retransmit for the entire flight of packets starting from the base to the packet right before next seek none. And the fourth transition is this: when the sender received a feedback and it's a corrupted feedback, then we do nothing. So this is just like in RDT 3.0, when the sender receives a corrupted ACK or a duplicate ACK, which is a negative ACK, it does nothing. Okay. Now the difference here though is that it only handles the corrupted ACK case. What happened to the duplicate ACK? In go back and sender, yeah, it's actually handled here. When the sender receives an ACK, it's now corrupted. Whether it's a new ACK or a duplicate ACK, the actions are the same. If it's a new ACK, the base will shift to the right. But if it's a duplicate ACK, if it's a duplicate cumulative ACK, the base will remain the same. Right? Would this be a problem? Now, some of you might not be very comfortable with this, right? Because, hey, if the base remains the same, what do we do here? Yeah, we'll be definitely in this situation, right? Yeah, there's an un-ACK packet somewhere and the base remains the same. We'll be restarting the timer, meaning the first time that base is receiving an ACK for all the packets before the base, the timer for that base has already been started. And now we're reassigning the base to the same value and restart the timer. That means we're extending the timer interval for that base. How do you like that? Think about it. And the last bit of the go back and sender, or shall I say the first bit of the go back and sender that we actually talked last, is the initialization of the sender. Okay, so the base, starting of the window, is initialized to sequence number 1. Next seek num is also initialized to sequence number 1. So this is unlike the RDT 3.0 sender receiver, always starting from packet sequence number 0. In go back and sender, textbook authors decide suddenly that they want to start from the sequence number 1.
All right, so that's the sender side of sender side of go back in's finite state machine. Now, finally, the receiver side.
Now, the receiver finite state machine of go back in. It's actually quite simple. Let's just skip the initialization and focus on the 2 transitions possible. Among the 2, this one is the more straightforward. We receive the data, get a call from below, and check the data, it's not corrupted, and check the sequence number of the data. Has seek num there is a function newly defined for go back in again. So what it does is simply checking the sequence number in the data and See if it matches the expected sequence number, which starts from sequence number 1. So if we receive packet 1 and it's expected, extract data out of packet 1, pass the data up to the application layer, generate ACK packet for packet sequence number 1, send the ACK out, increment the expected sequence number. Okay, so this is the simple case where everything works as expected. No error, no loss. And the second case is the default transition. What default meant is just all the other conditions that's not matching the previous transitions condition, which means the data can be corrupted or the data received not corrupted but not carrying the sequence number expected. So here, corrupted data or data packet that's not in the expected sequence number. Now this could be a duplicate data packet. This could also be a data packet carrying the future sequence number. So in either case, which means default is just to send the same packet again. That is the packet generated here, which is the ACK packet that is generated previously when data arriving correctly and in sequence. So in case of corrupted data, out of order data, we discard the data, no receiver buffering, so there's no extract of data, no passing of the data up to the application layer. And all we do is simply react to the data with the highest sequence number arriving correctly in order. So go back and receiver there. Works a bit odd, not that intuitive, but it's very simple. It always acknowledges to the data packet that is the highest in sequence number for all those who arrive correctly and in order. So all the receiver needs to track is the expected sequence number. And that's pretty much all. At the sender side, if a duplicate ACK is received, that is essentially saying either the data previously sent is corrupted or the data previously sent is lost.
All right, so that's the receiver end, right? Unless there's an expected sequence number data received. Otherwise, the ACK being generated are over from the default, which is a duplicate ACK. Okay, I know some of you might be wondering, hey, I thought the benefit of doing cumulative ACK is such that you need to send just one ACK for a flight of packet. But it turned out that the receiver end is sending new ACK or duplicate ACK for every data, whether there's a gap or not. There's just going to be an ACK going back. So the cumulative ACK is probably not working exactly the way you are imagining. Well, hey, let's go through a go backend example to make sure that we are familiar with go backend's sender side and receiver side finite state machine. Okay, and this example is a little bit hard. It's very simple. The example is very simple, but because of the complexity or the non-intuitive nature of go backend, it will take a longer time to walk you guys through the example. So it'll be in two parts. Okay, first part.
Next is to walk through an example of go backend following the finite state machines. So then we go back and recap, go back and sender's finite state machine and the receiver finite state machine, just so that you can follow. And real quick, the sender side of go backend is this. If we get a call from above, we check real quick whether next sequence number is within the sending window, which is base plus n. If it is, okay, then we generate packet and send it out. And then check whether we should be starting a timer. And the condition to start the timer is if this next seq number is indeed, okay, the base, and then increment the sequence number. All right, so check whether the next seq number is within the sending window. If so, generate the packet, send it out. Check whether we should start the timer. So next seq number, whether it equals the base, and then increment the next sequence number. If we do not pass the condition where the next seq number is within the sending window, then ask the application layer process to wait. All right. Now, back to the example. Let's assume the window size is 4, okay, and the sender's application layer process is sending data all the time. So sender here gets call from above all the time. So let's see. In the first call from above, all right, base and the next seek number are both initialized to 0. Okay. Now the first call from above is going to trigger, checking whether the next seek number is within the sending window. Sending window starting from base and window size is 4. Next seek is initialized to 0. Is 0 less than 0 plus 4? Yes. So we generate the packet, send it out. And next what? Check whether we need to start the timer. And the condition to start the timer is only when the next seek number equals the base. Next seek number is 0, base is 0. Cool. Okay. Packet 0 is indeed the first of the first flight. So start the timer here. All right. And next is just to increment the next seek number to what? 1. So next sequence number here at the beginning is 0. Now increment it to 1. So if we get a call from above again, next seek number, is it less than base, still 0, plus 4? Yes. So generate packet 1. 1 here is the next seek number, isn't it? Send it out. Check whether we should start the timer. Next seek num is 1. Base is 0, not matching. So the second packet in flight does not start timer. All right, just increment the next seek num. So here, the third call from above will start from next seek num equal to base 0 and 4. Is 2 less than 0 plus 4? Yes. So we generate yet another packet. Next seek num equal to, send it out. Do we start a timer? Next seek num equal to base 0, therefore not matching, not starting timer. Increment the sequence number to 3. Right? Is 3 less than 0 plus 4? Yes. Generate packet 3, send it out. Not start the timer because next seek number is 3 and base is still 0. Right? And we increment the sequence number to 4. And now we get the fifth call from above. And that call from above will check, is 4 less than base 0 plus 4? It's no longer less, right? So what do? We go to the refuse data part of the if condition. So yeah, the application layer process is asked to wait, and sender will pause sending for now. And these packets will go out to the internet and hopefully reaching the receiver, while there's a timer that's ticking and ticking, ticking, and that is associated with the base, the packet 0. All right. And here's to quickly review the receiver go back in. If we get a call from below, the data is not corrupted and carrying the expected sequence number, simply extract data, pass to the application layer, generate the ACK, send the ACK, and increment the expected sequence number. And otherwise, just resend the ACK that has been generated previously. Now, the receiver. Okay, receiver here will be receiving packet 0. Yeah, it's not corrupted and it's expected, right? So expecting sequence number 0, receiving sequence number 0. Therefore, we send ACK, expected number 0. Next, yeah, we get a call again from below, packet 1, not corrupted, and it's in sequence. Therefore, we send ACK for the highest data number that has correctly arrived and arriving in order. So these are being sent back to the sender. But packet 2, is lost somewhere on the internet. But packet 3 will arrive. It's not corrupted, but is it expected? We're actually expecting what? Sequence number 2. So we do not extract data. We actually trigger the default transition, if you recall, and just resend the ACK that is previously generated. So ACK 1 is being sent again. So right here. All right.
Okay, so that's the first part of the example. Now only 3 ACKs will come back. 2 of the ACKs, the earlier 2, are new, and the third one is a duplicate. Okay, let's see how the sender side will react to that.
And now we come back to the sender side. Okay, we'll be receiving ACK 0 here. All right. So receiving ACK 0, it triggers sender finite state machines. Oh, the transition at the bottom, isn't it? Receiving a call from below. Yeah, receiving a feedback packet from below. What do we do there? Yeah, let's recall and go back. Yeah, so here, quickly recall. Okay, this transition, getting a packet from the lower layer, and it's not corrupted. What do? Set the base to the sequence number in the ACK packet plus 1. And then we check whether we need to stop timer or refresh the timer. Now, only when the base and the next seek num are equal, then we stop timer, because the base here is empty, meaning no yellow packets at all, because next seek number is the first blue. So only when the base and the next seek number are the same. Otherwise, restart timer. Okay. Now we can come back here to examine. Yeah, what is the action the sender should be taking? Okay. First, receiving ACK0. So that's triggering the transition at the bottom, a feedback coming from the lower layer, and it's not corrupted. So what we do is to extract the sequence number in the ACK, add it by 1, and that will be the new base. So base here is moved by 1 position. The next thing we do is to check whether the base equals the next seek num, right? If they are the same, that means we should stop the timer, because hey, all the data packets are already added, right? But otherwise, then we restart the timer. So hey, base is 1, next seek num was previously 4, isn't it? That's why we are waiting here. Okay, so we cannot be stopping the timer. Instead, we should what? Restart the timer. So this timer here, original ticking, will be canceled, and we restart the timer here. And that timer is going to be associated with the new base, which is 1 over here. All right. And then, hey, sender is trying to send data. So quickly get a call from above. So we trigger the top transition. Right? So next seek num is 4. And 4, is it less than the base 1 plus the window size 4? So together 5. 4 less than 5. Cool. We can generate packet 4 and send it out. Is the sequence number base equaling the next seek num? No, so we do not start timer here. All right, so base is 1, so that means base, there's already a timer running. All right, next seek num, 4, not equaling 1, so not starting a timer here for generating packet 4. So timer is still associated with the base 1. All right, and then we increment the sequence number by 1, so 5 here. Similarly, receiving ACK1, we set the base to 1 plus 1. So the base is now what? 2. Is the base identical with the next seek num, which is 5? No, therefore we do not stop timer, but instead we restart timer. So T removed there, and T is restarted with the new base, that is 2 over here. Okay, so T for 2. So this is T for 1, and this is T for 0. And at this point, 1 slot open up, getting call from above. Yeah, 5 is less than 2 plus 4, 6. Therefore, we generate packet 5 and send it out. And do we start the timer? No, right? And increment the sequence number to 6. And yeah, another ACK1 is coming in. Okay, this is triggered by receiving packet 3 without packet 2. So ACK1 comes in, triggering the bottom transition, not corrupted, set the base to 1 plus 1, 2. Well, that is the same. All right. Base and next seek number, still not matching, therefore we restart timer. So hey, we actually kill the old timer for base 2. Now, restart timer for base 2. That means, well, this base is actually, waiting a longer time to expire to retransmit. But it's okay. It will still work. Just wait a bit longer. Right. If we get a call from above now, next seek is 6, and base is 2. 2 plus 4, also 6. 6 not greater than 6. Therefore, we again wait here. All right. So, yep, pretty much wait here. And so this timer for the base 2 is going to tick, 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 tick. All right. Let's assume packet 4 and 5 arrive at the receiver side, which generates re-ACK of packet 1 because they are out of order. And let's just assume these 2 ACKs is just going to take a long time to come back before T for 2, the second time here, times out. Okay. What's going to happen here is that it's going to trigger the sender side, the timeout event. What do we do there? We restart timer and what? Retransmit the entire flight of packets starting from the base. So 2, 3, 4, 5 go out at once. All right. And good thing is that at the other end, the receiver here finally gets packet 2. Yeah, it's finally the expected sequence number, so it's going to call the transition on the right, extract data, pass it up, so deliver to the application layer, and therefore we generate ACK2. And packet 3 arriving here, extract data, and then generate ACK3, and so on and so forth.
All right, so that was go back in, a full example. And we'll talk about the second pipeline RDT, selective repeat. And first is the introduction video.
Selective repeat. This is the second big categories of the pipeline RDT. So its design is pretty much the opposite of go back in. So in go back in, you have cumulative ACK. So the sequence number in the ACK there is to indicate all the packets before these particular numbers are received correctly. But in selective repeat, the acknowledgements are individual. So one acknowledgement packet per data packet. The sequence number in the acknowledgement is only to acknowledge one data packet. In go back in, we have one timer for an entire flight of packets. When that timer times out, we retransmit the whole flight of packets. In selective repeat, the opposite. We have one timer per data packet. When that timer times out, we retransmit just that data packet. All right, so receiver will acknowledge each correctly received data packet individually. Sender will only retransmit a packet when the timer for that packet expires. Very straightforward. The slight tricky part of the selective repeat is at the receiver. Okay, we now have to buffer packets arriving out of order. And the reason for this is very straightforward, very simple. If we send packet 1, 2, 3, and 1 arrive at the receiver, 2 get lost, 3 arrive at the receiver. You cannot be just extracting the data bits out of packet 1, pass it out to the upper layer, and not passing the bits of packet 2, and immediately pass the data bits in packet 3, and then later pass the data bits in packet 2, because that way you get bit sequences that is out of order in the application layer. And our definition of RDT is that all the bits arrive reliably and in order. So receiver here in selective repeat, the implementation gets complicated. You need memory space to store temporarily the packets arriving out of order. You wait until all the gaps are filled, and then you pass all the data bits up to the application layer in sequence. The only thing that remains the same is there is still this sending window, which is limited by n, from the base to base plus n. Now, be a bit careful in selective repeat though. What we are limiting there is the sequence number of the unact packet. So what is the maximum sequence number there can be unact. As opposed to in go back n, we say n being the number of unact packets. The reason that I'm saying you need to be careful is because of this. From the base to n plus base. Yeah, there are yellow packets, all right, and after the yellow packets, the blue packets. In go back n, they're just gonna be yellow and blue. So the number of yellow packets maximum will be n. In selective repeat, because we have individual acts, so some of the yellow packets can be green, like this. All right. So even though they're turned green, but that doesn't mean that they will include these 4, okay, into the window, like this. Okay, no. So what we're restricting is the maximum sequence number that can be unact, not the maximum number of packets can be unact. Okay, just to make sure that's clear. And the receiver of selective repeat is, as we talked about, more complicated. It also maintains a certain data structure, tracking the status of these packets. So we also have a window size here at the receiver. The base is now called the receive base. So receive A is always pointing at the first packet expected but not yet received. Right? And there could be a number of these pink packets around. So these are the packets arriving okay, but out of order because there's a gap before it. So those are the out of order buffered packets. The blue ones are reasonable, okay, packets that are expected next. Okay. The black ones are just not possible. So if we receive packets after receive base plus n, we'll be just treating these as maybe hackers injected packets, spoofed packets, things like that.
All right, so that was the introduction. So in a way, you can think of selective repeat being having many parallel RDT 3.0. Okay, a pair of data and ACK. Okay, but it's not exactly right. N numbers of these stop and wait RDT, because this N here needs to be consecutive. So when a packet out of sequence is acknowledged, you cannot advance the window. Okay, it's possible that you cannot advance the window. Okay, so it's somewhat like a unparalleled sessions of RDT 3.0, but not exactly, because the sequence number needs to be bounded within the N. All right. And next, what's missing here? Yeah, as selective repeats mechanism, it's better described, and it's described more robustly in finite state machines. So let's check out the FSM.
And now the selective repeats finite state machines. This is the sender side of the machine, and this is the receiver side of the machine. And you might be going, wait, they don't look like FSM at all, right? Because previously we have like states, right? And the number of transitions like these. Yeah, what I'm doing here is to do textual representation. So what I'm saying is essentially, yeah, there are still 3 transitions. So first transition is triggered by this event, the data from above. Okay. Second, the timeout event. Third, triggered by receiving an acknowledgement packet within a particular range. Yeah. So later on, you will see what's nice about writing the finite state machine this way, because it looks almost like a pseudocode, isn't it? Right? So the sender side is looking like a switch procedure, where when there's the data from above event switching in, then we do this. When there's the ACK packet being received switching in, then we do that. So now let's go over the finite state machines of the senders and receivers. Sender side, when there's a call from above, okay, if the next available sequence number is within the window, yeah, send packet. And you know how to do the next available sequence number, whether it's in window check, right? So the next seq num should be less than base plus n. Second is the timeout event. If our timer times out, and that is for packet sequence number n, we retransmit packet n and restart timer. Straightforward. If we receive an acknowledgement packet, we extract the sequence number and check if it's within the send base and send base plus n subtracting 1. So that is saying, hey, whether the ACK is within the reasonable range, right? Because the send window is only this big. If we receive ACK before that or after that, that's just weird. Okay, let's just ignore those. So we'll only be handling ACKs that's within the send window. Now, once that's the case, we mark packet n being received, so turn it to green. If n smallest ACK packet, so if n here is also the smallest ACK packet, so we turn that into green. There could be a number of other greens following that. Then we could what? Advance the send base all the way to the next yellow packet. Okay, so advance the window base to the next yellow packet, which is the next ACK packet. All right. So this is sender's actions, depending on what's triggering the sender's finite machine to take transitions. Similarly here at the receiver end, there are 1, 2, 3 transitions. First transition is if we receive a data packet that's within this range, the receive base and receive base plus n minus 1, so that is reasonable, okay, as expected. Then we send individual acknowledgement. So if it's packet n, then ACK n. If this packet is not expected, so meaning it's out of order, then we will buffer them. So these will be the pink packet, all right? Now, if this packet is actually coming in and filling one of the gray packets, so unreceived previously, but expected, then we can pass all the packets suddenly in sequence, all in pink, up to the application layer. So that's deliver those, okay, in ordered, and advance the window to the next, not yet received, but expected packet. So to the next gray packet. All right, so this is when we receive a data packet that is within the receiving window. If we get a packet, okay, that comes in, but it's actually in this range, receive base minus n to receive base minus 1. What is this? Okay. We are actually sending an egg for that packet back. If you recall, it could happen, right? The egg packet going back to the data center, if that packet is corrupted, the sender there is going to wait until the timer for that packet times out, then retransmit the data again. But that data has already been arrived at the receiver previously. And that's why the receiver sends an egg back to the data at the first place. And that's before the data is found corrupted at the sender as well. Right? So in that case, we still need to send the egg for that packet. Okay, do not ignore this. Otherwise, that timer is going to fire it again and again and again, and the sender there is going to retransmit the same packet again and again and again. Right? Third transition, otherwise, or the default, I'll just ignore. Okay, so receiver pretty much do nothing in case it's packet not within the receiving window or not one receiving window before. So those that are outside, just ignore it, because chances high that they're coming from hackers or previous connections, and the data somehow, the packet somehow gets stuck in the network for too long, and it's gonna be useless anyway.
All right, so that was selective repeats, finite state machine, and you see that finite state machine, pseudocode, these are two different ways of describing a computational process. And you know what? The ancestors of the finite state machine and the pseudocode are the Turing machines. Okay, that's what Alan Turing was saying, that I can actually represent all the computation process, okay, computational process with a machine like that. Okay, and it's actually abstract, a thinking machine. All right, so back to selective repeat. Let's check out also an example, just like every other former versions of these RDTs.
And let's also walk through an example of selective repeat, just like we did one for go back in. So that example in go back in is actually harder to analyze. This one, on the other hand, relatively easy. Now it looks very much like the example in go back in. So window size 4, and we start from base 0 and the next seek number 0. Getting a call from above? Yeah, because the next seek is less than base plus 4. Therefore, we generate packet 0 and send it out. And we go on until we hit next seek equals 4. And that is not smaller than 0 plus 4 anymore, so we wait. All right. Now, over at the receiver side, the scenario similar, receiving packet 0, but the receiver's action different. Okay, for packet 0, we send individual egg 0. Receiving packet 1, we send individual egg 1. Well, not getting packet 2, but we'll be getting packet 3. And out of order, so we buffer and send individual egg packet, egg 3. So egg 1, egg 0, egg 1, and egg 3 will go back to the sender. Now, sender, upon generating packet 0, packet 1, packet 2, and packet 3 will all start the timer individually. So T0, T1, T2, and T3 will all be ticking, no worries. Okay. Now, egg 0 now comes back to the sender. Sender receiving egg 0 will do what? Clear packet 0. So that packet will turn green. All right. Is it in sequence? Yes. So we advance window. Advance window by 1 to the next unegged packet. Upon receiving packet 1, also, advance sequence by 1 because it's in sequence. And hey, so base is changed to 1 and then to 2. So that allows us to send packets more, right? So 4 is generated, 5 is generated, and they're being sent out. Well, packet 2 did not get acknowledgement, but we get what? ACK for 3. All right. So what do we do there? Yes, we actually release packet 3. So we turn that into green. But hey, packet 2 there is still yellow. All right, so this green packet, packet 3, is not the smallest unact packet. So we cannot advance the window size further. We cannot advance the send window further or the base further. All right, so cannot be sending more. So still wait here. Okay, so this part of go back in and selective repeat similar. Right? But now, look, packet 4 and 5 will go to the receiver. Receiver here receiving 4, out of order again, buffer, send ACK 4. Packet 5, buffer again, send ACK 5. And those will go back. Here, timer for 4, timer for 5 will be fired because there's one timer for individual packets. Okay. So finally at this time point, timer for 2 finally expires, and therefore we resend packet 2. Packet 2 goes out, received. Finally, this is the smallest unact packet, and all the packets subsequenting packet 2, 3, 4, 5 can be passed up, okay, in sequence to the application layer, and we send back ACK for 2. All right. So simpler.
All right, and there's one more, actually, in fact, 2 more examples about SR, but those 2 examples are to illustrate the relationship between n, the window size, and the sequence number space. There needs to be some tricks you play setting the sequence number space according to n. Otherwise, you might mess things up. So here's it.
The last bit of selective repeat is this. Let me show you this case. There are 2 scenarios, okay? But from the reviewer's point of view, they will actually look the same, right? And this is due to the fact that the sequence number here, the sequence number space, and the window size there is not set in a way that we could tell individual packets apart. Those who are sent earlier versus those who are sent recently. Okay, so the example goes, sequence number, only 2 bits, so there are only 4 different numbers. Window size, 3. Right. So the selective repeat sender side will look like this. Well, the window size is 3, so we can only send 3 packets back to back of each other. So packet 0, packet 1, packet 2 goes out. Receiver here receiving 0, 1, and 2. They will then send back ACK 0, ACK 1, and ACK 2. So ACK 0 here arrives back at the sender first. And this is in sequence, so we advance the send base. And we generate yet another packet to go. All right. And the next ACK, that's going to advance the send base further to 2. All right. And we generate yet another packet to send. And the next one will be what? Carrying sequence number 0. Now, if packet number 3 did not arrive at the receiver, all right, receiver here will see, all right, I got the packet 0. And you know what? Within my window, I am indeed expecting someone carrying sequence number 0. So this one will be what? Buffered. And an ACK of 0 being sent back to the sender, isn't it? All right. So that seems to be fine. Yeah, this is the no problem case. Wait until you see the next one. Here's the next one. Same scenario, window size only 3, and we have sequence numbers. There are only 4 of them. So we send packet 0, 1, and 2 out. Receiver here generates ACK 0, ACK 1, and ACK 2 back. But unfortunately, all of them are lost. So timeout is going to happen and retransmit packet 0. This packet 0 will go, and receiver here will say, hey, you know what? I'm expecting packet 0. It's within the receive window. So buffer and send back ACK for 0. Sounds familiar, isn't it? Because that's exactly what's being done here in the first scenario. So from the receiver's point of view, identical. Also, buffer the packet and send back ACK0. But the thing is this, at the sender side, you see, this packet 0 is a retransmission of the first packet 0. But this packet 0 here is actually the second packet 0, no longer the original, the first packet 0. All right? So if packet 3 here arrived at the sender is going to what? Clear that gap and pass 0 up to the application layer. Before that, pass, of course, packet 3's bits into the application layer. So 3 and 0's data bits will go to the application layer. But look here. Now, this is packet 0. When packet 3 finally comes here, it's going to clear and send packet 3's bits as well as this retransmission 0's bits up to the what? The application layer. So you get unwanted duplicates. So you do have a situation here. From a receiver's point of view, it actually sees no differences in the two scenarios. You get duplicate data in the end in case B. So we need to be careful here to prevent. Packet 0 here and packet 0 here obviously are two different packets, but being confused as the same packet. Okay, so according to case A, we'll actually pass packet 0, these bits again to the application layer. Not good. All right? So in order to tell this packet 0 and this packet 0 apart, we have to think, what is the worst case? Okay, can we use a sequence number such that we will not be confusing this packet from this packet? Okay, so a new packet should be farther away, should be carrying a sequence number that's farther away from an earlier packet. And no worries, if you look at this, case number 2, case B here, is already the worst case that I'm illustrating. So in this case, we're seeing that the receiver is advancing the receiving window one after another. So the receiver is saying, hey, everything is okay, let's move on. But sending side here, not getting any X back, hesitates and waits and waits and waits and not moving. So you have one end moving really fast and the other end staying. Okay? So you see in the end, the worst case is what? The sending window never really moved, but the receiving window moved the entire end. All right? So they are actually end apart. If you want to make sure that none of the packets still in the sending window will be confused with the packets in the receiving window, what do you need to do? Is it obvious? The sequence number, make sure that the space is larger than 2 window sides, right? Then, hey, packet sequence 1 will never appear again in the next window, in the receiver's window. All right? So you will never have the trouble of confusing an old packet from a new packet. And that is why the sequence number space here needs to be larger or equal to 2 times the window size.
All right, so that's it for today. But don't go yet. Apologies from overflowing the time a little bit. Quiz 22. Yeah, this is to sum everything up about the pipeline RDT. Okay, so you'll be asked to do this, telling Polly which one you prefer. Okay, which of the pipeline RDT would you prefer, would you use, and more importantly, why? Okay, and the 4 scenarios you need to take into consideration in case the network bandwidth is really scarce. Which one would you use and why? In case the sender side memory is limited, which one would you use and why? Similarly, if the receiver side memory is limited, which one would you use? Last is in case you're hired to program a pipeline RDT. And of course, you want it to be minimum effort, right? If you are going for minimum effort, which one of these would you choose and why? Okay. And again, this is a take-home quiz. So go on, go get lunch, right? And you have 2-3 days of time to work on quiz 22. And that's all for today, guys. Thank you for the patience. And here is the time I say goodbye. Okay, bye. Okay, bye. Yeah, sorry for run over the time a little bit. Okay, bye. Okay, bye. All right, Polly's ending the stream now.